How do you even begin to understand a system that's so complex you can't see how it works on the inside? Well, sometimes the best way is to take it apart, piece by piece. Today, we're going to dissect this powerful technique that AI researchers use to peek inside that black box. It's called an ablation study, and it's how we're starting to really understand the artificial minds we've built.
And you might be surprised to hear this, but the core idea here isn't new at all. Actually, to really get it, we need to rewind the clock, way back, from today's artificial neural networks to the original biological ones. Okay, so picture this. It's the 19th century, and a physiologist named Pierre Florence is tackling one of the biggest mysteries out there, the brain. And his method? It was surprisingly direct. He would literally surgically remove a small part of an animal's brain and then just watch, see what changed. If an animal couldn't see properly after the surgery, he could pretty confidently connect that specific brain region to vision. A little blunt maybe, but it was one of the very first ways we started to map the brain, linking a physical part to a specific job. Now, let's fast forward to today, and AI researchers are facing a strikingly similar problem. Our modern neural networks are the new black boxes. They're incredibly powerful, but often they're just as confusing as the biological brain once was. So, what do? We've adapted the exact same principle. To understand them, we start removing parts to see what breaks. So what does this actually look like in the world of machine learning? Let's nail down a precise definition for this really powerful technique. It's pretty straightforward, really. In the AI world, ablation is just a fancy word for removing something. An ablation study, then, is the experiment you run after you've taken that piece out. The whole entire point is to answer one simple question: what did that part actually do?
And yeah, this visual here nails the process perfectly. You've got your complete network chugging along. Then you perform the ablation. Maybe you snip out a neuron, or even a whole layer. Then you test it again. But, and this is crucial, for this to work at all, the system needs what we call graceful degradation. Think of it like a car engine, right? If you pull out one spark plug, the engine might run rough, but it doesn't just explode. The network has to be able to keep functioning even if it's doing a bad job, for the study to tell you anything useful. Okay, but you might be thinking, why go through all this trouble? Why would you intentionally break a model that's working perfectly fine? Well, it turns out there are two really critical reasons for doing this.
The first big reason is to figure out what's important and what's not. The best analogy is a game of Jenga. You pull out a block, which could be a feature, a neuron, or a whole layer, and you see what happens. You measure just how much the model's performance drops. If you pull out one piece and the whole tower comes crashing down, well, that piece was obviously critical. A huge drop in performance means that whatever you just removed was super important.
And the second reason, well, this one goes even deeper. It's about basically reverse engineering the model to get its internal logic. By systematically taking out parts, you can start to map out how and where it stores knowledge. You can test how robust it is by finding redundant parts that are kind of like backups. And you can make it way more efficient by finding and pruning away the parts that aren't really doing much. All of this helps us build better, leaner, and most importantly, more transparent models. Okay, all this theory is great, but let's see it in action. A real-world case study is where this stuff really clicks. We're going to look at a network that was designed to recognize handwritten digits. All right, so here was the setup. Researchers trained a neural network on a super famous data set of handwritten digits. Their big goal was to figure out the role of each individual neuron. And to do that, they performed what they called single-unit ablations, which means they painstakingly removed one single neuron at a time from a hidden layer, and after each removal, they measured the hit to the network's overall accuracy. So first things first, you need a baseline. You gotta know how well the thing works before you start breaking it. And the complete untouched network was really accurate. It was getting the digits right almost 95% of the time. So that's our before picture. Okay, so what do you think happened when they removed just one neuron? One single neuron. What kind of damage could one tiny little component possibly do? And wow, no, that is not a typo. Taking out one single neuron, which they called Unit 12, completely crippled the entire network. Its accuracy plummeted by almost 45%. This is a stunning discovery. It means a huge chunk of the model's critical knowledge wasn't spread out. It was all concentrated in one single point of failure. You break that one point, and the whole system just collapses. But here's where it gets even more interesting. Not all neurons are created equal. When they took out Unit 19, it almost exclusively messed up the network's ability to recognize the number 1. It's like they found the one neuron. But then there was Unit 6. When they removed that one, almost nothing happened. Performance barely budged. That neuron was basically dead weight. the perfect candidate to be pruned away to make the model leaner and faster. So this stuff is fascinating in a lab for sure, but it has huge real-world consequences, especially when the stakes are really, really high. I mean, just imagine a black box AI is controlling billions of dollars in a financial market. You have to know how it works. You just have to. Ablation studies let you do that. They help you justify why a model is built the way it is, they help you debug it when it goes wrong, and they help you prove to regulators that you actually understand your own system. It's all about turning a risky black box into a transparent tool you can actually trust.
And you know, this all leads to a much bigger idea. It's almost a philosophical one. This technique isn't just about debugging. It's about adopting a more rigorous, more scientific approach to how we build AI.
The AI pioneer Francois Chollet just nailed it with this quote. An ablation study is really an honest effort to disprove your own model's design. By systematically trying to break it, you're challenging the assumption that every single part is necessary and that you understand it. It is a form of scientific self-critique.
So that's really the bottom line here. Ablation studies are a surprisingly simple, yet incredibly powerful method. They let us move past just seeing correlations and start actually probing for causality inside our models. They are a fundamental tool in the whole quest to build AI systems that aren't just powerful, but also robust, transparent, and in the end, trustworthy.
And that kind of leaves us with this final big question to chew on. As we build these ever more complex artificial minds, the willingness to carefully, thoughtfully, and scientifically break them apart might just be the most important skill we have. It begs the question, what are we willing to break in order to truly understand what we've built?